Welcome back for our lesson on part 2 of chapter 28 on magnetism. Let's talk about the motion of a charged particle in a magnetic field. In this case, what we said last time was that magnetic forces do no work on a particle. Let's look at some of the motion in more detail. Suppose I have a positively charged particle moving in a uniform constant magnetic field with some initial velocity vector that's perpendicular to the field. And let's assume that the field is into the board. So using that first right-hand rule that we've learned, the charged particle is going left to right, and I've got a field going into the board, there's going to be an upward force on that particle. And what it's going to tend to do then is to make it change its motion as it's going in through the field. So it's going to go like this, and then it's going to move like this, and like this, and like this. And as you can see, the end result is going to be that the particle itself will undergo uniform circular motion, which is kind of interesting because it would suggest to you that we can bring centripetal forces into this at some point. So indeed what's going on is the magnetic force is acting like a central force, which changes only the direction of the velocity vector, but not the size of it. So this is what we call uniform circular motion. As such, I can write that force as Q times V, because V and B are perpendicular, so I don't need the cross product. That's equal to 1. And that's going to be equal to the centripetal force that the particle feels as a result of this magnetic force. If I do that, I can very easily calculate the radius of that motion. Just move, a little bit of algebra shows that this is going to be equal to mv over qb. Oftentimes we call this radius a cyclotron radius, because this is one of the ways that we produce this kind of motion in a cyclotron, where we accelerate charged particles. So notice that the radius is proportional to the momentum of the particle. Kind of an interesting relationship. Other properties, we can calculate an angular frequency. Omega is V over R, and in this case, using our variables, I can write that as QB over M. So this is an angular frequency. And of course, we can have an angular period, T, which is equal to 2 pi over omega. And so that's going to be 2 pi M over QB in these terms. So you can see this once again, as we said before, the centripetal force is a fictitious force. It's not a real force on its own. It's caused by some other force. We've learned how tension can do that. We've learned how gravity can do that. Now we're learning how magnetic fields and magnetic forces can do that. If I have a nice uniform motion of a charged particle, I'm going to get this nice uniform circular motion. And so that's a very simple and probably the only kind of calculation you'll do that deals with uniform circular motion in a magnetic field. We can make the motion more complicated. So for example, suppose we have a charged particle that moves in a magnetic field, even if it's a constant magnetic field, but we do it at an angle other than 90 degrees. And if that's the case, we might have a case where the charge will undergo helical motion. So the motion will be like a helix if the field is not exactly perpendicular to the direction that the charge is moving. Again, we will not be doing problems that entertain this kind of motion. Generally, the problems that we do in this chapter will be dealing with uniform fields perpendicular to the direction of motion. We can do things like talk about the bending of an electron beam in a magnetic field. One reason to do that is to measure the strength of a magnetic field. So let's look at the following example. suppose we have an electron beam and we're accelerating electrons through a potential of 350 volts. Okay? We have a uniform electron beam and it has a radius of 7.5 centimeters, and the magnetic field is perpendicular to the electron beam, so that makes things very easy. First thing we might want to do is let's find the magnitude of the magnetic field. Well, we know that we can do that because we know that the energy I can write as 1/2, if it's an electron beam, 9.1 times 10 to the minus 31 kilograms for the mass of the electron times the velocity squared. And I know that that energy is equal to the charge of the electron, 1.6 times 10 to the minus 19 coulombs, times the number of volts, right? Because this is going to give me, this is 350 volts, or 350 electron volts if I'm talking about an electron. The total number of joules then is when I take the product of the charge of the electron times the potential difference. That will give me an energy. In this case, it's a kinetic energy because the electron is moving. I can calculate the velocity from that, and if I do, I'll find that the velocity of the electron being accelerated through that voltage is going to be 1.1 times 10 to the 7 meters per second. The magnetic field then, I can write as using my expression for the cyclotron radius of this motion. I'm given the radius there, and I know if I've calculated the velocity, I know the mass, I know the charge, I can then calculate the magnetic field that the electron is moving in by saying, well, B has got to be equal to mv divided by q times r. And given that m is 9.1 times 10 to the minus 31 kilograms, and the velocity is 1.11 times 10 to the 7th meters per second, and I divide by the charge of the electron, 1.6 times 10 to the minus 19 coulombs, times the radius, which was given as 0.0075 meters. Is that right? 0.075 meters, sorry. My magnetic field then would be equal to 8.4 times 10 to the minus 4 Tesla, or 8.4 Gauss if you like those units better. I can also calculate an angular frequency. We can just say that that's V over R. Angular frequency, omega is equal to V over R. We calculated V as 1.1 times 10 to the 7 meters per second. The radius was given as 7.5 centimeters. If I put those two in, I'm going to get 1.5 times 10 to the 8th radians per second as an angular frequency. One other thing that I'd just like to mention before we move on from here, and I believe we've probably talked about this before, but if I have a non-uniform magnetic field and I have charged particles moving in a non-uniform magnetic field, the field is much more, the motion of the particle is much more complex. But there are some techniques that are used to take advantage of this motion. One is called the magnetic bottle. The magnetic bottle uses non-uniform magnetic fields to try to confine charged particles. This is used in an effort to control fusion. Now, there have been a lot of experiments that have been conducted to try to do this. Nobody's been successful yet. If they could, we'd probably have utility bills that are pennies per month. But unfortunately, we haven't been able to master that yet. There is a lot of work going on in trying to find a way to confine fusion, confine the charged particles. Magnetic bottle is one of the one of the principles that they use, and to us it's a fairly simple principle. It's just a matter of using the proper non-uniform magnetic field to try to confine these very energetic charged particles. I'd like to bring up a couple of other things that go with the applications of motion of charges in a magnetic field, just to touch on a few things. One is fairly fundamental. Maybe not that useful to us in solving problems at this point, but it's one that you kind of want to put in your memory bank for future use. This is called the Lorentz force. And that's if you have a charged particle, a moving charged particle, in both an electric and a magnetic field. As you might imagine, the force would be just the combination of that particle due to the electric field and then due to the magnetic field. So this is what we call the Lorentz force law, and it's very simply just the sum of the electrostatic force on the particle and the magnetic force on the particle. One application of this is you can use this, you can take advantage of this force, and by arranging or adjusting the sizes of electric and magnetic fields, you can choose the velocity of a stream of particles. And the way you might do that is to use something called the velocity selector. What a velocity selector will do is take all those particles, give them the exact same velocity, and so you can do further experiments, like use the mass spectrometer for these particles. So what you might do is you take a pair of charged plates that would create an electric field. So maybe you got plus and minus. Now I've got an electric field that points vertically downward. Okay? And then what you might do is apply a magnetic field perpendicular to the direction of the board. And what that will do then is, if I have positive charges, the electric field will make them point downward, but if I have positive charges in a magnetic field, the magnetic field will make them point upwards. And so I'll have essentially zero force on these particles, such that the magnetic force, the size of the magnetic force will be equal to the size of the electric force, which will cause each particle to have the same exact velocity. It's kind of a very nice trick, and in fact, what we would do is just say that the magnetic force is equal to the electric force, or vice versa. That being the case, we find that the velocity that I can produce is just the ratio of the electric field that I produce and the magnetic field I produce. So I can choose then, as long as I judiciously adjust my electric field and magnetic field, I can get the velocity of particles of my choice. Very useful. As I said, one of the applications for the velocity selector is in the device called the mass spectrometer, which is used in chemistry generally to separate different ions of the same element by having them take different curves because of their different masses. So, and you can read more about the details of the mass spec in your textbook or in chemistry texts, as you will. Other applications of this certainly might be the cyclotron. Again, you can read about those applications in your text as to how the basic principles behind how a cyclotron works in accelerating charged particles up to very, very high energies to cause collisions, and then for us to be able to probe what's inside these particles. So those are two fascinating applications of moving charges in magnetic fields. And that's all we have to say about charges moving in external magnetic fields. Where we would like to go in the next step is to talk about the magnetic fields that moving charges produce. And I think maybe we'll leave that until the next lecture. Thank you.